So I'm going to do a bunch of examples from 6.3 when we do that separable equations, separations of variables. I'm just going to plug some of them out of our book. So we're still in 6.3, separation of variables. Now, not every equation can be solved like that, of course, and it's one of the simplest ways to solve differential equations. So when it works, it feels really good. Now, in general, a general form of a differential equation that can be solved by separation of variables, something like this. You have a function of x, and then you have a function of y, dy dx, equals 0. So if an equation is in this form or can be manipulated into this form, we can solve it by separating a variable. So let me do a few examples just to show how that works. So I want to do question 8. Getting too fancy. Oh, well, good. Yeah, I have you on another sheet. So, all right, well, does that fit our little description over there? Actually, not really. Well, sure. I mean, I can rewrite it. I can remanipulate it. I can make it 1 over y. Right, I can do that. Can I? So that'll work. But let's just, the whole idea here, if we don't get hung up on that standard form, is to, again, as we did it on Wednesday, is to separate where all the y's on one end with dy and all the x's on the other end with dx. And, well, can we do this algebraically? You really have x dy dx equals y. So, as before, we'll just divide both sides by y, divide both sides by x, and multiply by dx. We'll get dy over y equals dx over x. Do you see that? How we're able to accomplish that? Just algebraically. So from here on, you do something to one side, you do the same thing to the other side. We'll integrate both sides. So these are nice little integrals, right? What's the integral on the left? On the y, on the right? Technically, I need absolute values. The integral of 1 over y is natural of absolute value of y. It's not that big of a deal if we don't put, very good, plus c. Let me just do it this way, plus a constant. Don't write it down like that. But you're right. We need, well, both sides have a constant, and then you move them on to one side. So it's easier just to have one side has a constant. Does that make sense? Because technically you do two integrals. I'm going to do my magic pen. It should be like plus c1 and then plus c2. So you subtract the constants from both sides. You still end up with the one constant on the end, right? That'll disappear. What? Magic. I'll have to go. I'll have to go faster than I go now, and I hear it's fast. Now, constant plus c. I can make that constant anything I like, as far as I'm concerned right now. And for the future simplification, because when you have a natural log, it'll be really convenient if I express this constant as a natural log as well. What I mean by that, instead of writing plus c, I'll write plus natural log of c. That's a constant, right? Right, c can be negative, but think about this. This could be any number. Because what's the range of a natural log? It's all real numbers. So whatever you think that constant is, I can always express it as a natural log of, this. Does that make sense? So that's a very valid point. I mean, if I had some kind of a range restrictions on the natural log, then I won't be able to do that. I have the domain restrictions, but I don't care because I needed to cover everything. The reason why I want to do that, because by the properties of, I'm just going to ignore the absolute value. I shouldn't be doing it that freely, but by the properties of natural logs, what can I do about this plus? Yeah, it becomes natural log of cx, right? So then automatically, again, by the property of natural logs, you have natural log of stuff equals natural log of stuff. Therefore, stuff equals stuff, right? That's one of the properties of logarithmic functions. Well, I mean, if we keep the absolute value, you'll get some well, I should probably do it all the way. I mean, what do we end up with? Y equals plus or minus cx? Is that kind of what you get? Why not? I mean, yeah, I know there, but as far as the x concerned, x could be. I mean, yeah, it'll probably you're gonna need some restrictions anyways to make that work to begin with, but I won't worry about it too much at this point. Your book kind of does it sometimes they decide to worry about the absolute value, sometimes they decide not to. I just really don't know what to tell you about that. It won't be that big of a deal if we just ignore it for now. Now, this little trick with the natural log, let me show you if we don't do that trick. We'll still get the same result. So let's say we have natural log of y equals natural log of x plus a constant, right? So how would you solve for y? Yeah, you'll do y equals e to the natural log of x plus c, right? Yeah, that becomes that becomes e to the natural log of x times e to the c, right? By the properties of exponents. So e to the natural log of x, that's x. E to the c is some constant, right? Whatever. So you still get y equals kx. So y equals constant x, y equals constant x. But this is kind of a lot quicker. So, I mean, if you use that, it's okay. If you don't, you'll still get to that point. Might be a little harder. Is that all right? Now, of course, if they give us some kind of an initial condition, we'll be able to go back and solve for that constant. How's that? Is that okay? All right, let's try number 14. Can you see those? That vertical bar is just there randomly appearing, so it has no meaning. It's not on the original page. So that seems to work, right? It kind of satisfies that. You have function of x and the function of y, dy dx. So again, our job is to flip everything around. So we have everything in terms of y on one side and everything in terms of x on the other side. Do you see how to do that algebraically? It's 12y dy dx equals 7 e to the x, right? What should I do? Yeah, multiply by dx, right? Get dx on the other side. So we have 12y dy equal 7 e to the x dx. So at this point, we can go ahead and integrate, right? So if we integrate both sides, what do we get on the left? 6y squared. What do we get on the right? 7 e to the x plus a constant, right? So technically, that's your answer. I mean, you can go ahead and solve for y. Now you're just going to get that plus or minus square root or whatever. But that's an answer where, solution is defined implicitly. But if you want to go ahead and solve for y, which you don't have to, y would be what? Plus or minus the square root. Yeah, 7 e to the x. You can write it like that, over 6. But, that's the idea. Is that fun? Okay. But it's pretty friendly, right? Again, the idea is to get them, get the variables to match. We're going to look at a few examples where it's impossible to do it the way the problem is written. So we'll have to do a little more preliminary work, do like a substitution of sorts. Just like not the same substitution, but the same idea where you make your expression more manageable by performing the substitution. Any questions on this one? You okay? Let's do one where we have to find a particular solution. So I was looking at number 20. Ugh. I just kind of caught a bit of a Here we go. Well, now it's at least you're not being distracted by other stuff. So I believe so. I mean, all right, nice and pretty. Let's focus on the radicals. So, okay, so it's a big mess. Well, let's try if we can flip it all around. So I'm going to do by writing y square root of 1 y minus x squared. I'm going to write this as dy over dx. And I'm going to kick the other side. I'm going to get that second expression to the other side. X, the square root of 1 minus y squared. Okay. So what should I do in order to get y's on one side and x's on the other side? Well, how? Yeah, just both sides by both roots, right? Just divide both sides by root 1 minus x squared, root 1 minus y squared, root 1 minus x squared, root 1 minus y squared. So these two cancel, and these two cancel, right? So you have y over the square root of 1 minus y squared, dy over dx, equals x over the square root of 1 minus x squared. Well, I can get dx on the other side, and I'm very happy, right? Y is on one end, x on the other end. It looks like I can do a substitution when integrating, right? Multiply both sides by dx. to get y over the square root of 1 minus y squared dy equals x over the square root of 1 minus x squared dx. Is that right? Are we ready to integrate? Well, I mean, but I have the, yeah, you have u 1 minus y squared du is negative 2y. It will work. Yeah, so you'll end up with like the integral of tangent. Yeah, but then what happens with del y? Well, not quite. You want to replace y with what? With sine? Okay, don't write anything down. If we do that, it will become right. So look what happens. You have a sine x over square root of 1 minus sine squared x, right? Times dy, which is cosine x dx, right? I mean, this is cosine, so those two cancel. So you'll end up with the integral of sine, so it's negative cosine, and then you have to. Here's in chapter 8 right now. That's what we're talking about. Yeah, but it's cosine squared. Don't worry, we're good. Is that okay? So you'll end up with the integral of sine x, right? So that gives you negative cosine x, and then you have to substitute back. How do we do that? Because your substitution was y equals sine x, so that means if this is x, what is sine? Yeah, so this is y, this is 1. So you end up with a negative square root of 1 minus y squared. Right? We'll get the same result, only we don't need to do that type of substitution. It's easier to do it with the traditional calc 1 substitution because that y plays well with the inside function. But you can do it that way, yeah, it will work out. It's a little bit over. You did that in calc 1? Yeah, but that's not that. I mean, if you didn't have y, then maybe. But you have that y. I mean, so this is called trigonometric substitution. We'll do this in chapter 8. It works, but it's easier to just do it with regular substitution. Because look, if I just do it this way, let me just do this integral on the left. Let u equal 1 minus y squared, right? So what's du? Negative 2y dy. So dy is du over negative 2y, right? So if we substitute, you'll get y over the square root of u, and then du over negative 2y. So y's cancel, right? Negative 1/2 is a constant. It can come out. And we're left with an integral of just u to the negative 1/2 du. Is that okay? So integrate that. You'll end up with negative 1/2. And then the antiderivative of this is u to the power 1/2 divided by 1/2. So it's times 2. So you get negative u to the 1/2 And when you substitute back, it's negative square root of 1 minus y squared. So that's exactly what you get doing the trig substitution. It's just, I think this is a little easier. You don't have to draw triangles. But it works. Okay? So this is a calc 1 integration, basic substitution. So the same thing will happen on the other side. I mean, if I integrate x over the square root, we'll get the same thing, right? It's the same integral. So after you integrate both sides, we'll end up with negative square root of 1 minus y squared equals negative square root of 1 minus x squared plus some constant, right? I mean, you can get rid of those negatives. They don't matter. And that's it. You don't have to go anything further. You don't solve for y. This is solution defined implicitly. Yeah, good point. We need to still solve for c, because that's what's the initial condition? 0, 1. So 0, 1. So I'll keep the negatives here. Negative of 1 minus 1 equals negative of 1 minus 0 plus c. So what do we end up with? 0 equals negative 1 plus c. So what is c? I mean, I can rewrite it like this. It's a square root of 1 minus x squared equals the square root of 1 minus y squared plus 1. So we don't have those negatives. Any questions on this? Right, so this is in a notation, yeah, this is y of x equals some constant. So x is 0 and y is 1. Other questions? Other questions there?
I was just going to ask what kind of word we use to ask the question.
Well, I mean, well, what can you skip? I mean, you can, I don't think you can skip the actual integration process here. I mean, sometimes you can just figure out the constant, but I don't think you can do it here, just in your head. I mean, you have to write it out. But, so that's about, I mean, I don't think there's any steps that you can omit.
Or you could like start with
Well, yeah, I mean, the whole algebraic part, you can do it faster and to get to this point. Is that what you're talking about? Yeah. Because sometimes those algebraic tricks will work faster. But do you understand what we're kind of doing here as far as splitting the variables, dy dx? What? Yeah. Let's try one more. 22. 22, what is it? So we'll capture those vertical bars. I don't know how to do that. But that's really all we're looking at. It's dr ds e to the r minus 2s. I'll just write this one. This one is a mess. So this was question 22. Did anybody remember the initial condition? Okay. So dr ds equals e to the r minus 2s and y of 0 equals 0. Okay. So right now, the way this one is written, the function on the right is a function of both r and s, and it's I mean, we'll have to use some properties of exponents to separate them. And what's the property that I can use? Division, very good. So dr ds is the same as e to the r over e to the 2s. Is that right? Okay. So now what do you want to do? Well, I mean, you can cross multiply and then divide again, but whatever. So you'll realize that e to the r will go in the denominator. It says dr over e to the r, right? And then ds will go in the numerator. It's ds over e to the 2s. Okay? So now we were able to separate the variables, so we should be able to solve this equation if we can actually figure out how to integrate this thing. So how do we integrate it? Well, then what's du? Yeah, write it as e to the negative r. E to the negative r dr, e to the negative 2s ds. Like this types of integration, I mean, technically you're supposed to use u substitution to figure out the constant, but you don't. I mean, you can, right? I mean, you can just figure out that what's the antiderivative of e to the negative r? Negative e to the negative r. Technically, you need to use the u substitution to find the negative sign in front of the e, but you can, I mean, I believe in your, right? How about the other side? Well, negative 1/2 e to the negative 2s, right? Because you need something to offset the negative 2. Now, plus a constant, technically. We might have to get a little, is that the case where I want to mess with my constants? Well, no, because I'm going to solve for that constant. Yeah, I can, because this is the place where I can find c, right? We have the initial condition 0, 0. So I can actually find c right now, and then I'll start solving for whatever variable I want to solve for. What is my function here? S, no, r, dr ds. So r is my function.
You didn't have the half-life say.
Yeah, you can do that. But as it's written right now, what is c? If you put 0, right, 0, 0. So this is negative 1 equals negative 1/2 plus c. So what is c? Negative 1/2. So right, all those negatives will eventually go away. So we have, if we get rid of all the negatives, it's e to the r equals 1/2 e to the negative 2s plus 1/2. Right? Negative r, that's right.
Well, yes.
Go ahead.
No, I was just gonna say if you multiply both sides by EDR, I think it's
Yeah, it will get rid of the negativity of this whole problem again, right? Which is suggesting if I do e to the, oops, if I do e to the r, e to the 2s, e to the r, e to the 2s, so on one side is just e to the 2s. On the other side is 1/2 e to the r, right? Oh, it's too messy now. plus 1/2 e to the r e to the 2s. So then if I try to solve for e to the r, so multiply by 2 e to the r, and then it's 1 plus 2 e to the 2s. Is that right? So e to the r equals 2 e to the 2s over all this. Is that kind of what you were talking about? So then r is natural log of all that? I think that works. I mean, how you do your algebra is really up to you. I mean, it's not the unique way of doing that. You might actually end up with an answer that looks a little more different. This is just the answer that doesn't have any negative exponents.
But you would be fine with leaving it as e to the negative r.
Well, it's in this case it's too simple to solve for r. I mean, if anything else, you can just take natural log of both sides and divide by negative. So you'll get r by itself. Just solve for r. It doesn't have to be in this form, this very form. It could be another form. But again, the most important part is to get to this point. I mean, just doing the separation of variables, integrating, having fun with that. Does that make sense? How we're doing this? Let me do a little problem like this. A little application of our ability to solve differential equations. So I'm not going to go into the details where it's applied. You'll see it in your physics and engineering course or whatever, but it's called orthogonal projections. And orthogonal, that's just basically a fancy way of saying perpendicular. You guys know about that, right? So here's an example. Let's say I have a family of curves x equals k y squared. Now what are those? What are the graph of x equals some constant y squared? Right, sideways parabola. So this is all sideways parabolas. Depending on the value of k, if k is positive, you'll get something like that. If k is bigger positive, you'll get something like that. If k is smaller positive, you'll get something like that. Right? So all possible parabolas facing that way, but if k is negative, you're going to end up with parabolas facing that way. It's a funny little picture. So what I'm looking at another family of curves where each curve is basically orthogonal to each one of those parabolas, or perpendicular in that sense. So that means if I have a curve that crosses this parabola, it forms 90-degree angles where it crosses. Okay, so if I kind of keep going with that, I mean, does that look like it's forming right angles? I mean, what does it look like that I'm getting? Something like that? Close enough. Not necessarily a circle, maybe an ellipse of sorts. But this is what I'm looking for. I'm looking for the family of curves that does that. Now, how do I even know whether the two curves are perpendicular to each other? What am I going to be looking at? Right, the angle, but how can I measure the angle there? I mean, there are curves. Well, I'll look at the tangent line, right? The easiest way for me to see, like, let's say I have this one curve and there's another curve. Well, a bad example, but what I'm really going to look at, I'm going to look at the tangent line to one curve and the tangent line to the other curve. And if these two tangent lines are perpendicular, then I'm very happy. Okay, so that means the two curves are orthogonal. Okay, so all of a sudden we're talking about tangent lines, and if we're talking about tangent lines, and we're talking about the slopes of tangent lines, we're talking about derivatives, right? And what do you remember about what? Why? No. If it's a horizontal line, then the derivative is 0. But this could be.
So would it be like the negative inverse of
Yeah, negative reciprocal, right? Whatever the slopes of the tangent lines to the parabolas, the slopes of the curves that we're looking for will be negative reciprocals of the slopes of parabolas. That's how we know that two lines are perpendicular. Remember that? The slopes of perpendicular lines are negative reciprocals of each other. Well, right. I mean, if your lines are always horizontal, then you know.
What if you said the derivatives of each curve equal to each other? They came out. If that came out 0, would that mean perpendicular?
No.
Because if that was 1 and that was negative 1,
Yeah, well, they're not 0, right? One. That's what I kind of want. I want one to be 1 and the other one negative 1, right?
if you like have the k of x, like it, a derivative of it should be 0.
I'm not sure I followed your question. What?
If you like for f of g of x, like you plug like one function, like one derivative, let's say like first derivative is 2x, and you plug that into the other one, which is like let's say negative.
Yeah, you'll get negative 1, right? That's what we know about the slopes of perpendicular lines. Their product is negative 1, or the composition of the derivative function should be negative 1, right? That's kind of, yeah. So, but we'll use that knowledge of negative reciprocals. So, but long story short, we're going to have to find, we're going to have to take some derivatives. Okay, we're going to have to set up basically a differential equation where derivative equals negative reciprocal of something else. Okay. So, yeah, well, let's, because basically, again, we need a derivative. So let's take, because right now our function is defined, I mean, I can solve for y, but I don't feel like it. Take d dx of both sides. So if I do that, what do I get on the left? 1. What do I get on the right? Right. So the derivative done implicitly 2ky dy dx. Well, k is just a constant in this case, because again, the only thing that k does, it tells me how the parabola, what parabola looks like. Either it goes left or right, things like that. Yeah, we'll just solve for dy dx. So dy dx equals 1 over 2ky, right? I can actually get rid of that k right now, because k is, I don't want to even think about that k, because I can solve for k, right? I know what k equals to. In this case, what is k? If I solve for k, x over y squared, I can actually use that to get rid of that k. So if I, what was that? X over y squared. So it's, yeah, so it's 1 over 2 x over y, so this is y over 2x. So then, well, what that tells me that I can find the slope of a tangent line to any one of those parabolas at any given point, you know? And every one of those slopes is given by this formula. Is that okay? Now, what would be the slope of those orthogonal, the perpendicular curves be? Negative 2x over, right? So therefore, the slope of what we're looking for would be the negative reciprocal, so it's negative 2x over 1. So here we go. By solving this differential equation, I'll get the family of curves that I'm looking for. So they'll have, I'm guaranteed to have, you know, the slopes at the intersections would be negative reciprocals of each other, which makes them perpendicular and so forth. Does that make sense? So again, the plan was, I mean, if I just really simplify what we just did, found the derivative, which is my slope, took negative reciprocal, which is the slope of the perpendicular tangent lines. Well then, we'll have to solve that, and that's would be the easier part here, right? How to go about solving this one? Yeah, because this will work, right? If I multiply, doesn't matter where you put a negative, so it's 2x dx equals negative y dy. Is that okay? If I do it that way? Integrate both sides. We're ending up with x squared equals negative y squared over 2 plus a constant. Or x squared plus y squared over 2 equals some constant, which is ellipse. How many L's in the ellipse? 2. Yeah, you can write it as 2x squared plus y squared equals some other constant. So 2c or k, whatever you want to call that. Yeah. And that's kind of what we thought would happen. How's that? Does that make sense?
And so that's your ellipse that solves, or that will give you a right angle.
Mm-hmm. So it gives me the.
What that k, you just say
No. This k and that k, you mean? No. They'll be related in some other way, but they'll be different, yes. So that's why we're using, so that example, g. You know, so some other constant. Okay. Want to try one more of these? What do you think?
Yes.
Yes? Well, here's the one that we can probably guess. Very simple case. What is the family of curves? Y equals kx. Yeah, just the lines go through the origin, right? So we can actually do that one. That didn't work. Oh no. I'll be more careful. So I have a bunch of lines that go through the origin, right? So what kind of curve is perpendicular to all of those lines simultaneously? Circle. So the orthogonal family would be just a bunch of circles, right? So we would expect to end up with something like x squared plus y squared equals, again, a constant for our answer, right? Want to see if we can do that? Because, I mean, we predicted the answer here. I mean, if we try to solve that one, I mean, that's, how do you, oh, you're way ahead of me. Are you getting that? I mean, if I just take the derivatives, right, k, is that right? And as before we said, k is y over x, so dy dx is y over x. This is getting fancy. So what are we getting? Dy over y? Is that right? No, not yet. I'm sorry. I'm forgetting one step. Yeah, the inverse. So the perpendicular line, so dy over dx would be negative, oh, that's better, negative x over y. Is that okay? The negative reciprocal part? So now if we do the separation of variable, we'll get negative x dx equals y dy. So yes, you integrate both sides, we'll get negative x squared over 2 equals y squared over 2 plus some constant. So it's a circle, right? I mean, if I get everything to one side, I mean, I can call my constant anything I like, but I can manipulate this into x squared plus y squared equals, I don't know, some other constant, p. Right, multiply by 2, and it's, so that works out. So yeah, don't forget about this step, to do the negative reciprocal. Let's try another one. How about this, where the product of x and y is some constant? So it's a bunch of these, right? So it's y equals, or a bunch of these. That's cool, I don't know. So in this case, I can actually, I'm just going to take a derivative as it is. I'm just going to kill k altogether, right? If I just take a derivative, k is gone. So if you just take the derivative using the product rule, so it's 1 times y plus x dy dx equals 0, right? Am I right?
That's right.
What was that? So solve for dy dx, so you have x dy dx equals negative y. So then dy dx is negative y over x. Is that okay? So what do I need to do with that? So that's the slope of those hyperbola-looking things. Yeah, so the perpendicular slopes would be positive x over y. So I'll try to solve that one. I'll get y dy equals x dx, so I'll get more hyperbola-looking things. So we'll integrate both sides. We'll get y squared over 2 equals x squared over 2 plus a constant. I just put it over 2 so I don't have to make up a new letter. So if you just manipulate this thing, it's x squared minus y squared equals a constant. So it's a bunch of other hyperbolas. So it's kind of these ones. Right, so they will form 90-degree angles. All those ones too. Okay. I don't know if I want to do this example. So does this make sense, this process? Okay, you're going to have a few homework problems like that. I want to do this example. It's a fun little problem. Yeah, look at that. Let's do a coyote example. All right, so let's try to build this one from scratch. So what do we know? The rate of change of the number of coyotes presented by n of t is directly proportional to that, where t is the time in years, and then they give us a couple points. And we want to find the population when t equals 3. Okay? So this, we kind of talked about this terminology of being directly proportional. All we know right now that I can express it as dn dt, that's the rate, equals some constant, right, k, times 650 minus n. So that's what that first sentence means, the sentence from here to here. The rate of change of n is directly proportional to that expression. So that's what that means. Is that okay? So can we solve this equation? K is a constant, so we can do the separation of variables. We can rewrite it as dn over 650 minus n equals k dt. Is that okay? Now we integrate both sides. We're going to get a little natural log on one end. Right, so this is just a negative ln of 650 minus n. Population shouldn't be above 650, otherwise. On the other end, kt plus some constant. Is that all right? So we want to try to solve for n in this case, so let's get rid of that. Let's call it C1 for now. Let's get rid of the negative, so we have a natural log of 650 minus n equals negative kt minus C1. So to get rid of the natural log, we need to use the exponential function. So 650 minus n equals e to the negative kt minus c1, right? So to solve for n, I can add n to both sides, subtract e, so n of t equals 650 minus e to the negative kt minus c1. Is that okay? Now I can do this, and I should. This is 650 minus e to the negative kt times e to the negative c1, right? So this is just some other constant. Let that be c. So I can say that 650 minus c e to the negative kt. Okay, so this is my model. So in order for me to answer all the questions, I need to find what c is. I need to find what k is as well. K is the rate, and c would be some constant, so we can use some of those conditions there. Yeah, this one is easy, right? T equals 0, population is 300. That will allow me to find c, right? So the point 0, 300. So if I do that, it's 300 equals 650 minus c times e to the 0, right? So what is c? 350. And from here on, it becomes a college. I mean, this is already a college algebra problem from here point on, right? So now my model is n of t is 650 minus 350e to the negative kt. So I can find k because I have another point, 500, right? Is that right? So that'll allow me to find k. So plug in 500 for n. Yeah, right, negative 2k, thank you. So we can solve for k. I'm losing interest in this problem, but this is very algebraic at this point. Keep it up? Thank you. So what do I do next? You help me. Yes. Very good, yes. So 150 equals 350 e to the negative 2k. Then we divide. Divide by 350. Feels like I should be able to reduce it by, so 3/7, right? So what now? Take natural log. So it's negative 2k equals ln of 3/7. So k is ln of 3/7 over negative 2. Whatever that is. I mean, you can keep that as your rate. You can plug it in the calculator. So 3/7 natural log, make it positive, half it. So is that okay? Yes? If you want all those digits, then that's your rate. I mean, this is really a preferred option probably, that your model right now is n of t is, what was that, 650 minus 350 e to the negative ln of 3/7 over 2t. times negative what? There was a negative, right? So that's positive. There was a 2 as well? No, no, no. 2 is that t was 2. Yeah. So yeah, so plus. So if you want to do n of 3, you'll just, yeah. It's algebra question from here on, and it's been an algebra question for a while. Whatever that is. So this times 3 negative. I'll stop it. That's not what I'm getting. I got 552-ish. Is that what you said? Oh, you said 552. I just heard 152. I ignored the 5. 552. All right, so that's that. How's that? I know, not exciting. It was a cute picture of a coyote, that's why I was that. I want to do this one problem. We have time for that. And this is fun. I was messing with it yesterday. So here's an example. Let's just go back to just solving equations. Y prime equals x cubed plus y cubed over xy squared. Just solving these problems by the techniques that you were given is going to be problematic, because if I try to do this, if I try to do that separation of variable part, so it's dy over dx equals x cubed plus y cubed over xy squared, and I mean, let's just cross multiply this thing. I'll get xy squared dy equals the sum dx. And even if I try very hard, I don't think I'll be able to get just y's dy's on one end and x dx on the other end. What do you think? Can I do that? Because that plus is messing me up, right? On the right. I mean, I can get rid of the x on the left, but then how do you get rid of that y cubed from the right? You want to try? Could you repeat that?
X cubed over xy squared plus y cubed over xy squared.
Like, well, then I'm back to where I started, right? Yeah. Well, is that good? Try to separate that. I don't think it's going to work. It's a little messy. And this is one of those equations that when I look at this, it's of this form. I have some kind of a function of x and y, dy, plus some kind of a function of x and y, dx, equals 0. It's a function of this form. You see that? I have a mixture of x's and y's, and so forth. So it's slightly different from what we were doing originally at the very beginning of this class, when we just had functions separate. I mean, if I just do like, n of x dx, m of y dy. So here's what we can do, a little substitution. This is a little fun little trick. And I'm going to just do this problem. Maybe if we have time, we'll talk about what's actually going on in there. I'm going to make a substitution. I'm going to replace y with the following expression, vx, where v is some function of x still. V is a function. V is some v of x. V is a function of x. Okay? Now let's see what will happen. If I replace, instead of y squared, I'll put vx squared. Now instead of dy, if y is vx, then dy would be v dx plus x dv. I mean, I'll have to use a product rule of sorts, because v and x are both functions. Okay? So dy is being replaced with this expression now by the product rule, v dx plus x dv equals x cubed is x cubed plus, instead of y cubed, I'll put vx cubed, and dx is dx. So I ended up, I don't have any y's, but I have that extra v. Well, now let's see if I can do this one by separating variables. So let's do some simplification. X vx squared will give me v squared x cubed. Is that okay? V dx plus x dv equals x cubed plus v cubed x cubed dx. And just, I'm going to open up all the parentheses, see where that takes me. So if I distribute this, I'll get v cubed x cubed dx plus v cubed x to the fourth dv equals, oh yes, v squared, sorry, you're right. Equals x cubed dx plus v cubed x cubed dx. See, I didn't do anything silly yet. I just replaced every y with vx, and I'm just messing with algebra. The only tricky part was to realize that dv is this. I mean, I'm sorry, dy is that big product, the product rule. Yeah, that's a 4. Yeah, this whole thing goes away, right? That goes away. So you can actually now do the variable, you can separate the variables now. If you divide both sides by x to the power 4, you'll get v squared dv equals dx over x. Okay. We can do that one, right? So we have our variables separated. We have v's on one end, x's on the other end. So what do we do now? Yep, integrate both sides. Integrate. So this is v cubed over 3. What about the other side? ln of x plus a constant. Let's just do that ln of c. So it's easier later on. So v cubed equals 3 natural logs of cx. Is that okay? We just combine them. So v, you can say v is the cube root of all that. Right? Well, what is v? If we hopefully still remember, y equals v x, so that means v is y over x, right? So I can replace v with y over x. So it's y over x equals. So y is x the cube root of all that. How's that? You think you like that? So this is another example of substitution. It doesn't work every time by no means. We'll have to specify for which problem that works. I mean, if your problem is on this form, then you have a chance that this works. And these two functions have to be very special functions. They have to satisfy the following property. Here's a property. Let's say so anyways, these types of equations, we call them homogeneous equations, just like the word homogeneous you use in other walks of life. Milk, right? Sure. Probably no relation. I don't know why they use that word. So I don't know if I'm spelling this right. Am I spelling this right? There's no E somewhere, right? Yeah, that's right. Look at that. That's right. Homogeneous differential equations. So, few things. They're of the form where the functions n and m are so-called homogeneous functions. Now the definition of a homogeneous functions. What do we mean by that? Is the following. So definition, so a function f of xy is a homogeneous function if the following happens. If I make a substitution, if I make this kind of substitution, instead of x I put tx, instead of y I put 2y, somehow I'm able to factor out the t to some power, it could be t squared, t cubed, or whatever, times the original function. Okay? So this is actually called, if that happens, whatever the power of t that pops out would be the degree of this homogeneous function. So this would be of degree n. So if your both functions satisfy that, then this little trick that we did, and you can do that. You replace y with vx, and then you see what happens. Now, how we test whether functions are homogeneous? Like, you see, here are my two functions. Here's the n of xy, and here's m of xy, right? So if let's take the first one, and to see whether it works for that. So let's say if f of xy is xy squared, right? And I want to compute f of tx ty, so that becomes tx times ty squared. Is that okay? So if I further the computation, I'll get tx times t squared y squared, which becomes t cubed times xy squared. This is the original function. Right? So this actually will be a homogeneous function of degree 3. Whatever the power of t that shows up, that's the degree of that homogeneous function. Is that okay? Same thing with the other one. That other function was x cubed plus y cubed. So if I do the same trick, I mean, you can just see right away how t cubed will factor out. Right? I mean, if I replace every x with tx and every y with ty, then this happens. Right? So this is the original. Well, there are many places where it wouldn't work. I mean, if these two exponents, if this was x squared and y cubed, that wouldn't have worked, right? I mean, if I just change this ever so slightly, if I make this one if I do that, it won't work, right? Because if I replace, so I'll get t squared x squared plus t cubed y cubed. So the only thing that I can factor is t squared. Well, this is no longer the original function, right? So that, no, not homogeneous. Your book does this example x over y. If we do it here, tx ty becomes tx over ty. So t's cancel, right? So it's x over y. Did it work? Yeah, it's degree 0. I can always assume there's a silent t to the power 0 on the outside, so it's homogeneous of degree 0. I don't know how good that does, but it's there. Okay. So your homework is posted. Actually, how many of you are deep in that assignment? No? Okay, well, good, because I dropped a few questions from the end of this list, so if you printed it out some time ago, make sure you adjust it. Also, another upgrade or update to the syllabus